So, welcome all to another problem solving session from TIFR. So, today we will be dealing with this problem. So, which of the following statement is true or false? So, the statements are this, that A4 to Z modulo 4Z and A4 to Z modulo 3Z. So, which is what can we say about the surjectivity? So, the statement is this: there exists a surjective map, there exists a surjective map. So, if this is your statement 1 and this is the statement 2, then which of the following statements are true? So, this is a group theoretic question, and we will solve it like that. So, one of the things that you need to solve, that you need to know to solve this problem are this: if phi is a group homomorphism from G to G prime, if phi is a group homomorphism from G to G prime, then for some G in G, order of phi G divides order of G. So this is one thing that you need to know. Another thing that you need to know to solve this, if you want to solve it the way I am going to tell you, are the Silo theorems. Okay, so these are the two things that you need to know to solve this problem. So especially this corollary to Silo's theorem says that uh, a group of order k is a group of order n is normal if and only if it is unique in that group. Okay, so like there is only one subgroup of that order. If that happens, then only it is a normal subgroup. That's the Silo's theorem that we will use. It's that uh, uniqueness. Non. So this is the statement from the Silo's theorem that we are going to use. So see, if I take the first one, if let's assume that there exists a surjective map from A4 to Z4. All right, let's call it phi. So then this implies that kernel of phi, this has order. What should be the order of kernel of phi? The kernel of phi should have order 3, right? Because A4 modulo kernel of phi has to be isomorphic to Z4. So because of this reason, the order of kernel of phi, it has to be equals to 3. But since kernel of phi is a subgroup of A4 and it is normal, and kernel of phi is a normal subgroup of A4, then by Silo's theorem, it implies that there exists only one subgroup of order 3 of A4. So if our assumption was correct, then it implies that there exists only one subgroup of order 3 in A4, but which is not, because if you take order 3, then all the 3 cycles that are present in A4, you take the cyclic subgroup generated by them. So all those subgroups, I mean, you will always find two such subgroups which are of order 3. So thus, this assumption is not correct. Okay, because take 1, 2, 3 and 2, 3, 4. So if you take these two, so this cyclic subgroup is of order 3. This cyclic subgroup is also of order 3. Okay, so hence there does not exist only subgroup of order 3 in. This implies there does not exist any surjective map from A4 to Z. Okay, so now for the second statement, what you can do is something like this. So this takes care of statement 1, is it true or false. Now statement 2. So what is the statement 2? Statement 2 is this, that does there exist a surjective map from A4 to Z3? So this arrow means surjectivity. Okay. So now the fact is that yes, of course there is. How will you produce it? It's precisely by using this first section. So now see what are the orders of the elements of Z3. The orders of the elements of Z3 are, so orders of the elements of Z3 are 1 or 3, right? Because it's a cyclic group. So as you can see that what are the elements of Z3? So the elements of Z3 are 0, 1 and 2. Okay. So what are the orders of the elements of A4? So A4 is itself, A4 is of order 12. That means what? The orders are 1, 2, 3, 4. Okay. So these are the orders that the element might have in A4. Now the only problem is that with 4. Okay, so what should we do about this 4? Now this 4, the element of order 4 is this 1, 2, 3, 4 in A4. So what is the element that has order 4 in A4? The element that has order 4 in A4 is this 1, 2, 3, 4. So what is the surjective map? The surjective map is all the order 2 elements, all the order 2 elements. So see, the order 3 elements are precisely 1, 2, 3, 2, 3, 4, 1, 3, 4, the combinations of these 3 cycles. So all those order 3 elements will be mapped in either 1 or 2. Okay. The rest of them, if you take any element of order 2, if you take an element of order 2, then it has to be mapped to an element in Z3 which divides 2, which divides the order 2, right? So that means what? It will be it will be mapped to an element of order 1. So what is the element of order 1 in Z3? That is the 0. So now by this, what we will find is that there exists a surjective map from sorry map from A4 to Z3 whose kernel consists of 4 elements. So what are these 4 elements? 1, 2, 2, 3, 3, 4, 1, 4. So if you think about it, then if you take 2, 4, so you can kind of combine it, the 2 cycle, if you think about the 2 cycle, 2, 4, all these things will not be inside A4 because these are dispositions. So the order 2 elements that are present in A4 will be, I mean, are there any elements of order 2 that are present in A4? The answer is no, because elements of, so it's like this. So elements of order 2 in A4 are transpositions, thus not in A4. So then what will be the order 2 elements? The order 2 elements will be product of these type of things in A4. In A4 that are transpositions, thus not in A4. So the order 2 elements will be of this form. So how many such clubbings can you do? So this is 1, 2, 2, 3, 1, 2, 2, 4. This type of clubbings. Okay. So the order 4 element, that is of 1, 2, 3, 4. The only thing you need to check is that will this be inside A4 or not. Okay. But 1, 2, 3, 4 is, I mean, is it an even permutation or an odd permutation? But anyway, you have a surjective map from A4 to Z3, which has 4 elements in the kernel after clubbing these two cycles together. So thus there always exists a surjective map from A4 to Z3, whereas there does not exist a surjective map from A4. So where there does not exist a surjective map from A4 to Z4. Okay, so that's all for today. We will meet again with another problem next time. Okay, thank you for joining.